What's up, gamers? Guess who's back for another round of SI videos. In this video, we're going to be going over the topic of B-trees, otherwise known as balance trees. In the video, we will be covering the properties of B-trees, searching, and in essence, traversal of a B-tree, and the concepts behind B-tree insertion operations. So first off, we're going to go over some of the unique properties of a B-tree. For number one, all leaves will be at the same level. Number two, a B tree is defined by a minimum degree T, and this becomes important when looking at the example below. Number three, every node must contain at least T minus 1 keys, excluding the root, which can have at minimum 1 key. So essentially all this is saying is that there is a minimum key value for all children. So if you look at the bottom, you can tell that the root is of T equals 3. So at minimum, there's at least 2 keys within each leaf. Now, for number 4, there is a maximum. All nodes may contain at most 2t minus 1. In this example, that means a node may hold at most 5 keys. And this becomes important when you think of insertion. Number 5, number of children of a node is equal to the keys in it plus 1. In the example below, you can notice that there are 3 keys, and with it, there's an associated 4 children. Number 6, all keys in the node are in increasing order. What is also not included here is that all the items or the keys inside of the B tree will also be distinct. Now, number 7 is an extra property, is that insertion and deletion will begin at the root of a B tree as opposed to a leaf. And lastly, we have the time complexities for the search, insertion, and deletion, which is O of log n. Now, how does searching through a B tree work? In essence, there's really no real difference between what you've done before and what you'll be doing now. However, you can think of traversals more like an in-order binary tree traversal. Now let's talk about inserting into a B tree. I've set up an example for t is equal to 3. So let's go through this step by step. First of all, we're going to insert 10 into our B tree. Now that's not too bad, so let's make it worse. So now we're going to insert 20, 30, 40, and 50. Now if you remember one of the properties that we just went over recently, it's that we can have at most 2t minus 1 keys in a node. So let's overflow it. We want to insert 60. However, we can't because there's no room. So in order to do this, we'll split it at the median, and then we will insert 60. And as you can see, we'll have a set 10, 20, which will be the left child, since 10 and 20 are less than 30. And then we'll have 40 and 50 as the right child, for it is greater than 30. And because 60 is greater than 30, we will move it onto the side with 40 and 50. Now, if we add 70 and 80, we're finding ourselves into a very similar predicament that we just went through. So let's do it again. Now we want to insert 90. However, it's not possible because, if you remember, we can only have 2t minus 1 keys in a single node. So in order to split it, we're going to take the median. The median will go into the root. And now that we have 2 keys in the root node, we must have 3 children. So we will have 10 and 20, which is less than 30. We will have 40 and 50, which is greater than 30, but also less than 60. And then we will have a third child, 70, 80, which is greater than 60. And as you can guess, afterwards we can insert 90 at the end. Here's some oversimplified pseudocode to explain the tree insertion. And with that, that is the end of this video. If you have any questions, please come to our office hours. Feel free to email us or just drop a question in the comment section and we will do our best to get back to you. Well, with that being said, peace out, gamers.